June 24, 1944. Oak Ridge, Tennessee. General Leslie Groves just approved construction of a uranium enrichment plant that his own advisors said would take 6 months to build. He gave the contractors 4. Actually, scratch that. He wanted the first production unit running in just 75 days. Here's the contradiction that should be impossible. The Philadelphia pilot plant had exploded just weeks before, killing 2 men and injuring 11 others. The technology was still untested at scale. And yet, Groves was betting everything on a process that his Manhattan Project colleagues had rejected 2 years earlier as technically unfeasible. But this wasn't recklessness, this was desperation meeting innovation. Because by mid-1944, the atomic bomb project was failing. The massive Y-12 electromagnetic plant couldn't produce enough enriched uranium. The enormous K-25 gaseous diffusion plant was months behind schedule. And somewhere in the Pacific, American soldiers were dying by the thousands as they island-hopped toward Japan. The solution came from an unlikely source: the United States Navy. While the Army's Manhattan Project was pursuing billion-dollar enrichment technologies, a Navy physicist named Philip Abelson had been quietly perfecting a different approach. A method so simple it seemed almost primitive. Steam pipes and temperature differences, that's it. Today, you're going to discover how Navy scientists and a Cleveland construction company pulled off one of the most remarkable engineering achievements of World War II. How they built 2,142 vertical columns, each 48 feet tall, arranged them in 21 massive racks, and used nothing but steam, cold water, and physics to help end the war. This is the story of S-50, the thermal diffusion plant that almost nobody remembers, but that accelerated the production of the Hiroshima bomb by approximately 1 week.
To understand why S-50 mattered, you need to understand the uranium crisis of 1944. Natural uranium contains only 0.71% of uranium-235, the isotope that can sustain a nuclear chain reaction. The remaining 99.28% is uranium-238, which is essentially useless for building atomic bombs. To create a weapon, you need to concentrate uranium-235 to at least 89% purity. The challenge? These 2 isotopes are chemically identical. You can't separate them with chemical reactions. The only difference is 3 neutrons in the nucleus, creating a tiny mass difference of just 1.26%. The Manhattan Project pursued multiple enrichment methods simultaneously. At Oak Ridge, Tennessee, the Y-12 electromagnetic plant used massive machines called calutrons, based on Ernest Lawrence's cyclotron design. These devices used powerful magnets to bend the path of uranium ions, separating the lighter uranium-235 from the heavier uranium-238. The technology worked, but barely. Y-12 was plagued with problems. Magnets overheated. Vacuum seals failed constantly. Production crawled along at a fraction of the expected rate. Meanwhile, construction had begun on K-25, an enormous gaseous diffusion plant. This half-mile-long facility would push gaseous uranium hexafluoride through thousands of porous barriers, gradually concentrating uranium-235. But K-25 was a nightmare of its own. The barriers kept clogging. Corrosion destroyed equipment. By spring 1944, it was clear K-25 wouldn't be operational for months, maybe even a year. Robert Oppenheimer, the scientific director at Los Alamos, was watching these failures with growing alarm. The laboratory had the bomb design ready. They had the detonation mechanism perfected. What they didn't have was enough enriched uranium. Without it, the entire Manhattan Project would fail. $2 billion spent, 3 years of work, thousands of scientists, all for nothing. That's when Oppenheimer remembered something. Back in February 1944, he'd received reports about a Navy project in Philadelphia. A physicist named Philip Abelson was running thermal diffusion experiments at the Philadelphia Navy Yard. The process seemed crude compared to the sophisticated technologies the Manhattan Project was developing. But it had one massive advantage: it actually worked.
Philip Abelson was only 31 years old in 1944, but he was already a significant figure in nuclear physics. He'd been among the first American scientists to verify nuclear fission in 1939. The following year, he'd co-discovered neptunium, the first transuranium element. When World War II began, he turned his attention to uranium enrichment. Abelson's approach was based on a phenomenon discovered in the 19th century called thermal diffusion, specifically the Surret effect. Here's how it works. When you have a mixture of molecules and you create a temperature difference across that mixture, the lighter molecules migrate toward the hot side, while the heavier molecules move toward the cold side. German scientists Klaus Clusius and Gerhard Dickel had used this principle in 1938 to separate isotopes of neon gas. Abelson adapted this concept for liquid uranium hexafluoride. His design was elegantly simple: two concentric vertical pipes. The inner pipe, made of nickel to resist corrosion, carried high-pressure steam at 545 degrees Fahrenheit. The outer pipe, made of copper, was cooled by water at 155 degrees. Between these pipes was a gap measuring between 0.21 and 0.38 millimeters, barely thicker than a sheet of paper. Into this impossibly narrow space, Abelson pumped liquid uranium hexafluoride under pressure. The temperature gradient did the rest. The lighter uranium-235 molecules concentrated near the hot inner wall. Convection currents carried this enriched material upward. The heavier uranium-238 sank downward along the cold outer wall. Over time, slightly enriched uranium collected at the top of the column, while depleted uranium pooled at the bottom. But slightly is the key word. A single column could only increase uranium-235 concentration from 0.71% to maybe 0.75%. To reach weapons-grade purity of 89%, you'd need thousands of columns operating in series, each one feeding into the next. The mathematics were daunting. Abelson calculated that producing 1 kilogram per day of 90% enriched uranium would require 21,800 columns, each 36 feet tall. When Abelson presented this proposal to the Manhattan Project's S1 Executive Committee in January 1943, they rejected it immediately. The committee chairman, Edgar Murphy, ran the numbers. Such a plant would cost $32.6 million to build and require 600 days to reach equilibrium production. The operating costs would exceed $62,000 per day. They rounded up and declared the project would cost $75 million with no uranium production by 1946. The decision was final. Liquid thermal diffusion was dead. But Abelson didn't quit. With Navy funding, he built a pilot plant at the Anacostia Naval Air Station in Washington, D.C., using columns 36 feet tall. The results were promising but limited. In September 1943, he moved the project to the Philadelphia Navy Yard, where he had access to industrial-scale steam systems. The Philadelphia plant expanded to 102 columns, each now 48 feet tall, arranged in a single rack. The Navy wasn't interested in atomic bombs. They wanted nuclear-powered submarines. Admiral Harold Bowen saw thermal diffusion as a way to produce fuel for nuclear reactors. Inter-service rivalry also played a role. President Roosevelt had explicitly excluded the Navy from the Manhattan Project in March 1942. The thermal diffusion program became the Navy's way to maintain a stake in atomic energy research. But here's what they didn't know. That Navy project in Philadelphia, the one the Army had dismissed as impractical,
was about to become the Manhattan Project's lifeline because Robert Oppenheimer had just realized something that would change everything. On March 4, 1944, Oppenheimer wrote to James Conant, chairman of the National Defense Research Committee. He requested all available reports on thermal diffusion. When he studied Abelson's data, Oppenheimer saw what the S1 committee had missed. Yes, thermal diffusion couldn't produce weapons-grade uranium on its own, but that was never the point. The genius was in the system integration. If you ran the enrichment processes in series rather than in parallel, everything changed. Start with thermal diffusion to boost natural uranium from 0.71% to about 0.89%. Feed that slightly enriched uranium into the gaseous diffusion plant at K25, which could concentrate it to 23%. Finally, run it through the electromagnetic calatrons at Y12 to reach 89% purity. The mathematics were compelling. An electromagnetic plant that could produce 1 gram of 40% enriched uranium per day from natural feed could produce 2 grams of 80% enriched uranium from feed already enriched to 1.4%. You'd more than double Y12's output without building a single new calatron. Better yet, you could build a thermal diffusion plant quickly using simple construction techniques and readily available materials. On April 28, 1944, Oppenheimer wrote directly to General Groves with his proposal. The production of the Y12 plant could be increased by some 30 or 40%, and its enhancement somewhat improved many months earlier than the scheduled date for K25 production. Groves immediately grasped the implications. He'd been under enormous pressure to deliver results. The Manhattan Project had consumed over $2 billion with no finished weapon to show for it. Military planners were preparing for Operation Downfall, the invasion of Japan, with casualty estimates exceeding 1 million American servicemen. Any method that could accelerate uranium production, even by a few weeks, could save thousands of lives. On May 31, 1944, Groves appointed a review committee consisting of Murphree, Warren Lewis, and Richard Tolman to investigate Oppenheimer's proposal. The committee visited the Philadelphia Navy Yard the very next day. They watched Abelson's columns in operation. They examined the engineering specifications. They studied the production data. Their report concluded that Oppenheimer was fundamentally correct, though his estimates were slightly optimistic. Adding 2 additional racks to the Philadelphia pilot plant would take 2 months, but wouldn't produce sufficient feed for Y12's requirements. The only solution was to build a full-scale production facility. On June 12, Groves asked Murphree for a detailed cost estimate. The specifications called for 1,600 columns capable of producing 50 kilograms of uranium enriched to between 0.9 and 3.0% per day from natural feed. Murphy's team calculated the cost at $3.5 million for a 1,600-column plant. Groves approved construction on June 24, 1944. Now came the impossible part. Groves informed the Military Policy Committee that the plant would be operational by January 1, 1945, less than 7 months away. But even that wasn't fast enough. Privately, Groves demanded that H.K. Ferguson Company have the first production unit running in just 75 days, 4 months to build the entire facility. The scale of the challenge was staggering. The production plant would consist of 21 racks, each containing 102 columns. That's 2,142 columns total. Each column measured exactly 48 feet in height and 5 inches in diameter. The inner tubes had to be manufactured from nickel to tolerances of plus or minus 0.0003 inches. The spacing between inner and outer tubes required precision of plus or minus 0.002 inches. These tolerances were extraordinary for 1944 manufacturing capabilities. 23 companies were approached. Most declined immediately when they learned the specifications and timeline. Only 2 accepted: the Grinnell Company of Providence, Rhode Island, and the Mering and Hansen Company of Washington, D.C. took on the challenge of manufacturing columns to specifications that seemed impossible to achieve. The site selected was at Oak Ridge, immediately adjacent to the K-25 powerhouse. This location provided 3 critical advantages. Steam could be piped directly from the K-25 boilers. Cooling water could be drawn from the nearby Clinch River at a rate of 15,000 gallons per minute, and security was already established for the classified Manhattan Project facility. On July 9, 1944, ground was broken at the S-50 site. The S-50 was a security code name. Construction employment peaked at 1,900 workers in September. The facility required massive infrastructure. The main process building alone measured 522 feet long, 82 feet wide, and 75 feet high. It was painted black to reduce visibility from the air. Inside this structure, the 21 racks were arranged in 3 groups of 7. Each rack stood as a massive tower of 102 vertical columns. Running the length of the west side was a mezzanine with 11 control rooms, each for 2 racks. Adjacent to each control room was a transfer room containing the dangerous equipment for loading uranium hexafluoride feed and removing enriched product. The real breakthrough came when engineers solved the problem nobody saw coming, and it involved a decision that would haunt them just weeks later in a Philadelphia transfer room.
On September 2, 1944, disaster struck the Philadelphia pilot plant. At 1:20 p.m., Private Arnold Kramish of the Special Engineer Detachment was working in a transfer room with 2 civilian chemists, Peter Newport Bragg, Jr. and Douglas Paul Meggs. They were attempting to replenish a 600-pound cylinder of uranium hexafluoride when it exploded without warning. The blast ruptured nearby steam pipes. Superheated steam at 545 degrees Fahrenheit mixed with vaporized uranium hexafluoride, creating hydrofluoric acid. This chemical is among the most dangerous industrial substances. It penetrates skin instantly, dissolving flesh and bone while destroying nerve endings. Private John Hoffman ran through the toxic cloud to rescue the 3 men. Bragg and Meggs died from their injuries. Kramish and 9 others, including 4 soldiers, were badly burned but survived. Hoffman himself suffered burns, earning the Soldier's Medal, the Army's highest honor for valor in a non-combat situation. It remains the only Soldier's Medal awarded to anyone in the Manhattan District. The accident investigation revealed a critical design flaw. The cylinder was made of steel with a nickel lining instead of solid seamless nickel. Why? Because the Army's wartime procurement had preempted nickel production, forcing contractors to use composite construction. The steel couldn't withstand the corrosion and pressure. It failed catastrophically. This explosion happened just 69 days after construction began at Oak Ridge. 1/3 of the S-50 plant was already complete. The first rack had just commenced operations on September 16th. Groves had a decision to make: shut down construction and redesign the system, losing months of time, or press forward with modifications. Groves chose to continue. Colonel Stafford Warren, chief of the Manhattan District's medical section, developed emergency treatment protocols for uranium hexafluoride exposure. All personnel received intensive safety training. The Naval Hospital created new procedures for handling hydrofluoric acid burns. And critically, Abelson and 15 of his staff relocated from Philadelphia to Oak Ridge to train operators on site. By January 1945, all 21 racks were installed and ready for operation. The construction contract terminated on February 15th, with remaining electrical and insulation work assigned to local Oak Ridge contractors.
The main plant became fully operational in March 1945, exactly 9 months after Oppenheimer's initial proposal. But there was a problem. The K-25 powerhouse couldn't supply enough steam. As stages of the gaseous diffusion plant came online, competition for steam became critical. The solution required building a dedicated boiler plant for S-50. The Navy provided 12 surplus boilers, originally manufactured for destroyer escorts. These operated at 450 pounds per square inch instead of the original 1,000 psi specification. The reduced steam pressure lowered the hot wall temperature, decreasing efficiency. But the trade-off was worthwhile because the destroyer escort boilers were oil-fired and immediately available. A 6 million-gallon oil tank farm was constructed with sufficient storage to operate S-50 for 60 days independently. The new boiler plant was approved on February 16, 1945. The first boiler started on July 5th. Full operations commenced on July 13th, just 5 days before the successful Trinity test of the plutonium bomb in New Mexico. Operating S-50 required unprecedented precision. The Furcleve Corporation, a wholly owned subsidiary created by H.K. Ferguson specifically to operate the plant, employed 1,600 workers at peak in April 1945. The plant ran continuously, 24 hours per day. Each rack consumed 11.6 megawatts of power. The enrichment process worked exactly as Abelson predicted. In normal operation, 1 pound of product was drawn from each circuit in 285 minutes. With 4 circuits per rack, each rack produced 20 pounds per day. Production initially struggled due to leaks and shutdowns. In October 1944, S-50 produced just 10.5 pounds of uranium enriched to 0.852%. But by June 1945, monthly production reached 12,730 pounds. The integration with other enrichment plants created a cascade system. S-50 enriched natural uranium from 0.71% to 0.89%. This material fed into K-25's gaseous diffusion process, which boosted concentration to approximately 23%. Finally, Y-12's electromagnetic calutrons refined it to 89%, sufficient for weapons use. Total S-50 production reached 56,504 pounds of uranium hexafluoride. Historians estimate that S-50's contribution accelerated the completion of the Little Boy uranium bomb by approximately 1 week. That bomb was dropped on Hiroshima, Japan on August 6, 1945, containing 64 kilograms of enriched uranium. Less than 1 kilogram underwent fission, releasing energy equivalent to 15,000 tons of TNT and killing an estimated 70,000 to 80,000 people instantly. However, the biggest shock came after the war ended, when Manhattan Project leaders finally revealed what they really thought about the plant that helped end the war.
On September 4, 1945, less than a month after Hiroshima, Lieutenant Colonel Arthur Peterson recommended shutting down S-50 permanently. The order came through immediately. By September 9th, all production had ceased. The columns were drained and cleaned. Furcleve Corporation employees received 2-week termination notices. The shutdown was brutal and swift. Voluntary resignations had already reduced Furcleve's payroll from 1,600 workers to about 900. Only 241 remained by the end of September. Furcleve's operating contract terminated on October 31, 1945. The last employees were laid off on February 16, 1946. Responsibility for the S-50 buildings transferred to the K-25 office. Why the rapid abandonment? Economics and efficiency. S-50 had been built as an emergency measure, optimized for speed rather than operating costs. The plant consumed enormous amounts of steam and cooling water. Its enrichment factor was low compared to gaseous diffusion.
As K-25 completed construction and resolved its technical problems, liquid thermal diffusion simply couldn't compete. General Groves himself admitted the miscalculation. "If I had appreciated the possibilities of thermal diffusion," he later wrote, "we would have gone ahead with it much sooner, taken a bit more time on the design of the plant, and made it much bigger and better." Its effect on our production of uranium-235 in June and July 1945 would have been appreciable. That statement reveals the cruel irony of S-50. It succeeded brilliantly at its mission while simultaneously proving itself obsolete. The plant accelerated uranium production at a critical moment, but only because it was built quickly rather than optimally. A better designed facility would have been more efficient, but it would have taken longer to construct, negating its primary advantage. Starting in May 1946, the S-50 buildings found a second life with the United States Army Air Force's Nuclear Energy for the Propulsion of Aircraft project. Fairchild Aircraft conducted beryllium experiments there. Workers fabricated blocks of enriched uranium and graphite for reactor research. NEPA operated until May 1951, when it was superseded by the Joint Atomic Energy Commission Air Force Aircraft Nuclear Propulsion Project. The S-50 plant was disassembled in the late 1940s. Equipment was hauled to the K-25 powerhouse area, where it sat in storage before eventually being salvaged or buried. The massive black process building was demolished. Today, nothing remains at the site except historical markers and contaminated soil requiring ongoing environmental monitoring. S-50 remains the only production-scale liquid thermal diffusion plant ever built. The technology was never used again for uranium enrichment. Modern enrichment relies almost exclusively on gas centrifuges, which are vastly more efficient than any method available during World War II. A modern centrifuge cascade can enrich uranium to weapons-grade purity using a fraction of the energy and space that S-50 required. Yet the engineering achievement stands as remarkable. From concept to full operation in 9 months, 2,142 precision-manufactured columns, each 48 feet tall, operating simultaneously within tolerances measured in thousandths of an inch. A construction workforce of 1,900 building a classified facility under wartime conditions. An operating staff of 1,600 managing one of the most dangerous industrial processes imaginable, handling thousands of kilograms of corrosive, toxic, radioactive material.
The lessons of S-50 resonate far beyond uranium enrichment. This project exemplifies how innovation succeeds under constraints. Consider the decision-making process. The Manhattan Project initially rejected thermal diffusion based on theoretical calculations showing it couldn't produce weapons-grade uranium. They were absolutely correct. But Oppenheimer recognized that the wrong question was being asked. The question wasn't, can thermal diffusion produce weapons-grade uranium? The question was, can thermal diffusion improve the performance of our existing enrichment systems? By reframing the problem, an impossible challenge became a practical engineering solution. The timeline demonstrates what focused urgency can accomplish. When Groves demanded a 75-day construction schedule, experienced engineers said it couldn't be done. They were almost right. It took 69 days to get the first rack operational, actually 6 days faster than Groves demanded. The full plant took 9 months instead of the standard 18-month construction timeline for comparable industrial facilities. That acceleration came from eliminating bureaucratic delays, prioritizing critical path items, and accepting calculated risks. The integration approach pioneered at S-50 influenced modern industrial processes. The concept of cascading multiple different technologies in series, each optimized for a specific enrichment range, became standard practice. Modern isotope separation facilities use similar staged approaches, combining technologies that individually would be inefficient, but together create optimal results. Safety lessons were written in blood.
The Philadelphia explosion killed 2 men and nearly derailed the project. But the response, developing immediate treatment protocols and comprehensive training programs, established standards that protected thousands of workers at Oak Ridge. No fatal accidents occurred at the S-50 production plant, despite handling far larger quantities of dangerous materials. Perhaps most significantly, S-50 represents the power of inter-service cooperation, even when that cooperation emerges from rivalry. The Navy funded thermal diffusion research because they were excluded from the Army's Manhattan Project. That rivalry inadvertently created a parallel research program that became critical when the Army's methods faltered. Modern military operations now deliberately structure overlapping research programs, recognizing that redundancy and competition can produce unexpected breakthroughs. Today, uranium enrichment faces new challenges. Nuclear power generation requires low-enriched uranium for civilian reactors. Arms control treaties require monitoring enrichment facilities to prevent weapons proliferation. Modern centrifuge technology has made enrichment faster and cheaper, but also more accessible to nations seeking nuclear weapons. The technical problem that S-50 helped solve in 1944 remains politically contentious 80 decades later. If you found this story fascinating, subscribe to the channel for more deep dives into wartime engineering problems and the technical solutions that changed history. Next week, we're exploring how British engineers built the Mulberry Harbors, the artificial ports that made the D-Day invasion possible. 2 massive harbors, constructed in sections, towed across the English Channel and assembled under enemy fire. The engineering challenge that Winston Churchill called one of the most difficult and daring undertakings of the war. Hit the notification bell so you don't miss it. And if you want to explore more stories of innovation under pressure, check out our video on the Enigma code-breaking machines at Bletchley Park. How Polish mathematicians and British engineers built electromechanical computers that could break German military codes in minutes, processing millions of possible combinations. The S-50 plant lasted less than a year in operation, but in that brief window, it proved that sometimes the solution to an impossible problem isn't to work harder at the same approach. Sometimes you need to step back, reframe the question, and recognize that the inferior technology, used correctly, becomes the breakthrough that changes everything.